Okay,
All
yeah,
right, here we go.
trig derivative. All right, wait up.
So we're
Trig
live.
derivative identities.
There you go.
That's what
So
it is.
we're just put those on page 1 as well, so we have those to refer back to. So we're talking about let's see, BC Calc, and we're doing derivatives, lots of chain rule stuff, product, quotient rule, inverse, that kind of stuff. So without a calculator, find the derivative. So the chain rule says that I'm going to take the derivative of the outermost function. Notice I kind of have 3 different functions here, right?
Yeah.
So it's going to be the derivative of the outermost function with the innermost function unchanged, and then the derivative of the innermost function multiplied by that. That's essentially what the chain rule is saying. Let's see if you have the chain rule on here. Yeah, so here's the chain rule. The derivative of a function inside a function, a composition of functions basically, is you take the derivative of the outer function and leave the inner function unchanged, and then you multiply that by the inner function. And you can do that multiple times.
Yeah.
We're going to need that one. We're also going to need the derivative of the, what do we have, cotangent?
Yeah.
Cotangent is negative cosecant squared x. Negative cosecant squared x. Oh, nope, secant is what we want. The derivative of the secant is secant times tangent. So the first thing I do is I take the derivative of the outermost function. I'll try to color code this. The outermost function is secant. So the derivative of that is, again, going back, is secant tangent. So I write secant tangent. And I leave the innermost function unchanged, right? So the derivative is secant tangent, and then I put this back in here. 3x squared plus 1 to the 4th, 3x squared plus 1 to the 4th. Okay, that's the first part. So that's the derivative of the outer function times the inner function, and unchanged. And now I'm going to do that to this thing. I'll use blue because now I still have a function inside a function, don't I?
Yeah.
So I'm going to have to, what's the derivative of that blue underlined thing? Well, the derivative of that is going to be the derivative of the outer function, which is like u to the 4th. So it's u, it's 4 times whatever u was, that thing inside there, 3x squared plus 1 to the 3rd. And then finally, I have to multiply that by the derivative of the innermost function. Let's go with black with that one. And that's this one right here. So multiply that by the derivative of the innermost function, which is just 6x. And then maybe clean that up a little bit. We can take this 4 and that 6x at the very least and put them together and move all of that to the front. So that's 24x times 3x squared plus 1 cubed times secant 3x squared plus 1 to the 4th tangent 3x squared plus 1 to the 4th. I think that's as far as they would want you to go here. They don't want you to expand this out, do they?
Yeah.
They do or don't?
Let me see.
I would think not for that one. I don't really see that much of an advantage in expanding that out.
See, there's a Unit 3 review answers.
Yeah, do you have the answer key for this?
Yes, I do. So the derivatives was y. Do you want me to screenshot it in?
Oh, is it not, is what we have not correct?
I think it's close, but it's not like, wait up.
Yeah, just read it to me and tell me what it says, and I'll tell you if.
It's a long thing.
Oh, so are you saying that this is expanded out? Is that what he did?
Wait up. Let me just screenshot it in. what he got. So I think it was what we had originally. Yeah. Quotient.
I'm going to duplicate this slide so that we can use it for number 2 instead of trying to erase things.
Do you see it on your screen?
I do not yet.
So,
Did you say you put it in there?
yeah, I put
There,
it
now
in
I see
there.
it.
I don't know why. Oh, is it on there now?
Yeah, I see it now.
Okay.
Yeah, that's right. We did it right.
Okay.
We just cleaned it up a little bit. That's
Yeah.
all.
Yeah.
We just took this and made it. Yeah, that's correct. Good. Okay. So number 2. Let's do number 2 now.
I'm just gonna delete this answer because we already have it.
No, don't delete it. I created a new. I'm on page 3 now. I just duplicated it.
Okay.
So let's go with the derivative of this one here, number 2. So we're gonna do the chain rule. So the outer function is like u to the 5th. So the derivative of this for number 2, the derivative is going to be 5 times u to the 4th, because that's the derivative of that outer function. Does that make sense?
Yeah.
And then, so the inner function you just leave unchanged, 3x plus 1 over 2x plus 5. And then multiplied by the derivative of the inner function. And my inner function is right there. So the derivative of the inner function, I'm going to have to use the quotient rule. And the quotient rule, if you remember, is low d high minus high d low.
Yeah.
Right?
Oh, hi, Mike.
Am I saying that right? Low d
Yeah.
high. I made this mistake the other day. I thought it was low d high. And yeah, there it is. Low d high minus high d low. Someone else said high d low minus low d high, and I just did it and I made a mistake.
Yeah.
I realized
It's kind of easy to like, I feel like mess up because it's like too, I don't know what I say, like you say it fast.
Yeah. So low, I actually remember this from all the way back in high school. Low d high. So there's my low. The derivative of the high is 3 minus high d low all over low squared. That check out?
Yeah.
And then you can simplify probably this up here. So let me do that above it so we can see this would be 6x plus 15 minus 6x minus 2. Be careful with that negative. Make sure you distribute that negative in with the 2.
Yeah.
Okay, and so then the 6's cancel out, the 6x's cancel out, and so you're just left with 13 on the top. So your answer is just going to be 5 times 3x plus 1 over 2x plus 5 to the 4th times, what do we say, 13?
Yeah.
So actually, let me erase this. This is probably the better way to write it is, hold on one second, let me clear my screen off here. I've got something on it. So the better thing to do is, what was that, 13? 13 times 5 is what, 65?
13 times 5 is 65, yeah.
So writing like this, 65 times 2x plus 5 squared, that's better.
Mhm.
So I just kind of combined those together. This was 13 right here.
Yeah. Okay.
And I just did 13 times 5, and then I put this in the denominator. That looks nicer.
Yeah.
Put it that way. Now you could also simplify that even more. You could write this as to the 4th and to the 4th. Actually, this might even look better. You understand what I did there?
Kind of, yeah.
I distributed the 4, and the reason I would want to do that is because now I can see how those are the same thing.
Yeah.
So probably the better way to write this is 65 times 3x plus 1 to the 4th all over 2x plus 5 to the 6th, because those are the same factor. So there's 6 of them. So this is probably the answer that is on your answer key.
Yeah. It was like what he got was 5 parentheses 3x plus 1 to the 4th power times 13. and 2x plus 5 to the cubed. So basically, yeah. Wait.
No, but you just said cubed. I think he's missed something.
There's something different on the bottom root. I can see the 65 because it's the 5 times 13.
What are you telling me that his answer was? I'll write it over here. Or can you just screenshot and put it on there?
Yeah, I'm gonna just screenshot it. It's faster.
I'm looking back through it, seeing if I made a mistake. I don't think I did, though. Yeah, I don't see a mistake on mine. I think, I don't know, maybe you're just misreading it or something, but I don't think it would be to the third power on the bottom.
Looks like a 3.
Did you put it on there?
Yeah, and maybe it's just loading because it took like a few.
Yeah, sometimes I have to close it and open it back up for it to show up. Well, everything is the same except for the 3. How do they only get 3 there?
I don't know. That's what I'm confused about too.
You know what I think he did? I think his is wrong, actually.
He said he is wrong sometimes on his thing.
I believe it's wrong. I think he forgot to raise this to the 4th power. See, because 5 times 13 is 65, which I also have that there. But then this right here shouldn't be 3, I don't think.
Yeah.
Because look at what you're doing. Remember, you're doing the chain rule. So this is really, you got 4 here and 4 here. When you distribute this 4, you don't just distribute it to the top. It's the top and the bottom. They both get it.
Yeah.
So I'm pretty sure that mine is right and his is wrong.
Yeah.
I could be wrong though, but I think so. Maybe check with him tomorrow in class. All right, let's do the last one. So this is an E problem. So when you have E, do you remember the derivative of E? So whoops, y equals e to the x squared plus 5x. So the outer function is e to the u. That's your outer function. And your inner function is x squared plus 5x. So I take the derivative of the outer function. What's the derivative of e to the u?
U, is it u with power rule? Nah.
I think it's just e to the u.
Yeah.
I
Okay.
think it's e to the u du, in fact, is what, let's see if you have e on here. No, you don't have it on here, but
You want me to go look it up?
no, it's okay. I know what it is. The derivative of e to the u is just e to the u times du dx. So this is really just, you basically just get e to the u. And so my u is still x squared plus 5x. And then you multiply that by the derivative of u, or that top function,
Yeah.
the inner function, which is just 2x plus 5. So that's your answer. Usually you'd write the 2x plus 5 in front. Doesn't really matter. But there it is, x squared plus 5x.
Just check. Yep, that's right.
All right. So the next page,
It's more
we've got
derivatives.
more of the same.
Maybe
So
we
this-
should just do other things.
No, we can whip these out real quick. Let's do it.
I know, it's just it's like 23 problems overall.
Oh, okay. Well, we got time. You got an hour, right?
Yeah, I till 4:30. I just want to make sure we get like the harder things done. Maybe.
I'll just go through them quick, okay?
Okay.
So this is going to be quotient rule,
Yeah.
right? So the derivative is going to be low d high, which is e to the x, minus high
ID low.
d low, which is just 1, all over low squared. But now for this, a lot of times it's simplifying it that is harder.
Yeah.
So this is going to be e to the x times x plus e to the x minus e to the x all over x plus 1 squared. Those cancel. You just get x e to the x all over x plus 1 squared. Got it?
Yeah, that's easy.
Number 5 is the product rule. So the derivative of this is going to be, here's your first function, here's your second function. So for this, it doesn't really matter which order you do it in. If you do derivative of the first times the second, or the derivative of the second times the first, because you're just adding them. But for the sake of consistency, what does it tell you on your notes? I don't remember what it says.
It's derivative of the first times second times derivative of the first times
Correct.
second. Or
Okay,
plus
so we're
something.
going to first take the derivative of the first just to be consistent.
Mhm.
So the derivative of the first is going to be 9.
9, yeah.
So I'm
Yeah.
taking the derivative of that and multiplying it by the second, which is ln of x squared plus 5x
-1.
minus 1. I'm going to run out of space here quick. So
Okay.
I'll just erase that. I'll need it. And then I add to that the first term times the derivative of the second. So what's the derivative of ln x squared plus 5x minus 1? What's the derivative of ln x? If what's the derivative of the ln of u? You remember?
No, I don't. Maybe just ULN or
I believe
LNU?
it's 1 over u du. Do you not have that in your notes anywhere?
I might have it in my notes, but I just completely.
I'll just type it in. I'll type it in real quick.
My notebook's filled with a bunch of stuff that I've written down and forgot.
Yeah, I was right. It's 1 over u. It's 1 over u du. So the derivative of, if this is my y, I'm going to do this kind of on the side here, then the derivative of this is going to be 1 over that whole thing unchanged, because that's the derivative without it being changed, right? Times the derivative of that inner function, which is 2x plus 5. Make sense?
Yeah.
So that is the derivative of the ln of x squared plus 5x plus 1. So I'm going to multiply that up here. So it's 2x plus 5 all over x squared plus 5x minus 1.
That's a huge equation.
Yeah, that's kind of a mess. Now, do you have to simplify it? Probably not. This is probably okay just to leave it like this.
Yeah.
But you could clean it up a little bit by like taking what's in the top there and just multiplying it by 9x. Maybe that would clean it up.
It wasn't simplified after that.
It was not. That was it.
Yeah.
Okay. So good. I'll just leave it like that. There's your answer. And number 6, I'll do it in red. I'll sneak it over here.
Okay.
What's
What's the two equations separated exactly, or is it not separated at all? Like, is it meant to be a product rule here?
For number 5 or number 6?
Number 6.
No, number 6 is not going to be a product. It's going to be a chain rule, because I have a composition of 3 functions actually. The outermost function is the natural log, then the middle function is the sine, and then of 2x.
Okay.
So I'm going to take the derivative. Remember how I take this. I'm going to take the derivative. Let me color code this one. There's my outer function. So y, the derivative, is going to be equal to the derivative of the outer function with the inner function unchanged. Remember that derivative of ln of u is just 1 over u.
Yeah.
So I do 1 over sine 2x times the derivative of the inner function. And the derivative of sine is what?
Cosine?
Cosine 2x unchanged, but then I have to take the derivative of the innermost function, which is 2x. What's the derivative of 2x?
2.
2. So cleaning it up, I have 2 and cosine 2x on the top, and I have sine of 2x on the bottom.
Yeah.
And cleaning it up even more if I wanted to, what's the cosine over the sine?
It's cotangent.
That's right. So really, I could just write 2 cotangent of 2x.
Yeah.
And that is another way you could write the answer. That would be a little bit simpler.
That's what he put down.
Yeah.
2 cotangent.
Okay.
Yeah.
Makes sense how we did that?
Yeah.
All right. Next, victims.
Same stuff.
Same old stuff.
Sorry, I'm just want to go over the whole review so that I can practice it again and then
Yeah, it's a
all
good
my
idea.
tests.
I'm having a hard time editing this one.
Sorry. Do you want me to move it?
No, it's all good.
Okay.
I don't know why
Blocking out 7.
it was being kind of difficult. It's not letting me like make it smaller for some reason.
I can try to make it smaller.
Oh, here, this is good. I like it that big anyway. That's fine. Whoops.
Okay.
You can go ahead and mess with it. Yeah, you can move it around. Make it.
I'm done. I'm done moving it. I'm done moving it. I don't.
I'll get it. All right, there we go. Perfect. So this first one, again, we got a product rule, right?
Yeah.
So we're going to do y prime equals the derivative of the first times the second, so leave it unchanged, plus the derivative of the second, which is 3e to the 3x, times the first.
Yeah.
That makes sense how I did that?
Yeah.
And I kind of used the chain rule a little bit for the derivative of e to the 3x, but that's pretty easy to do. You just take the derivative of 3x and put it in front of e to the 3x. And so that's probably all you have to do. I mean, you technically could factor out something if you wanted to. I don't know if he wants you to do this. But if you were ever like actually using this, you'd want it to be in factored form, because factored form allows you to find the zeros more easily. So you'll notice that I can take a 3x squared e to the 3x out of both of them. And that leaves me with 1 plus x to the first. Now, he might not have written that on the answer key, but this is the way you'd want to see it.
Like factored out.
Yeah, because then you can see, oh, what are my zeros? My zeros are -1. There is no zero related to this because that's an exponential, and you setting that equal to 0 won't give you an answer. But there is, and then there's a 0 of multiplicity 2 at 0. So that would help you determine some different.
The x cubed kind of throws me off with the factoring.
So what I did, look what I took out of 3. See how both of these terms had a 3?
Yeah.
2 x's. So that's why I took x squared out, and there was only 1 x left here.
Okay.
And then I took out an e to the 3x in both of them.
Okay.
Did he write this as his answer, or did he leave it like this?
He wrote it as what you had it down as.
Yeah, so that's the better way to write it, and the reasoning behind it. Because when I was, if I was you, I would be like, well, how do I know I have to factor that? Why would I have to factor it? Well, technically you wouldn't have to factor it, but the most usable form of a derivative is when you put it in factored form.
Yeah.
Because remember, that's how you find derivatives help you find the max and min points of your original function.
And they are slopes, so you want to make the slope as simple as possible, obviously.
Yeah. Well, yeah. But I mean, the way you solve this equation, setting a derivative equal to 0, the way you solve that is by factoring typically.
Yeah.
And using the zero product property. All right, number 8's easy. You want to tell me what to do for 8?
You do like the u of like cubed, right?
Okay, so which is what?
So it's u cubed, so wait up.
So what should I write first?
Wait up.
You're right. What's the derivative of u cubed?
Oh, you do like 3 on the outside, right?
Mm-hmm.
You do 3 4x squared plus 3x minus 1 squared. Is it squared?
Mm-hmm.
Okay. Then you get.
And then multiply that by what?
So then you so is this where you do product rule exactly? This is where I get confused.
Nope. I just need the derivative of what was on the inside.
Oh yeah. That's 8x plus 3.
Yep. That's it.
And that's it, right? You can't
Yeah,
really
that's it. I
simplify
mean, you
it
could,
out.
like I said, you could clean it up a little bit by taking that 3 and multiplying it in, but you don't really need to.
Okay, yeah, that was easy. Okay.
Good. How about this number 9?
Just check if that was the answer. Yeah, that was the answer.
I'm going to need some space for number 9.
It's
So
only 2 functions, right? For this one?
it
It's
is,
not 3, right?
it is 2 functions,
So no
but
chain rule.
there's a function inside a function as well.
Is it the square root that's making it a function inside a function?
Yeah. See how
That's
the
basically
square,
x squared plus 1 to the half power, right?
that's right.
Is that what we should change it to?
Yeah, we can do that if that helps.
Okay. So is this product rule then?
This is going to be product rule.
So so it's 2, right?
Mhm.
2 and then times x squared plus 1 to the half power.
No, you forgot 2x. It's
Oh,
2x.
it's 2x. Oh, my bad. Okay, my bad. Sorry.
2x. There's the derivative of that blue one.
And then times the second function
Yep. Plus.
x squared. And then what do I do?
Plus x
Do
squared.
you do the same thing that I did for 8 basically, or do I?
Well, this is going to be a chain rule thing, right?
Okay.
So what's the outer function?
Is it half?
U to the 1/2.
Yeah. Okay.
How do I
So
take the derivative of u to the 1/2?
you put half on the outside
Mm-hmm.
and then x squared plus 1, right?
Yep, times u to the what power?
Negative half?
Yep. Good.
Okay.
That's it. Now for cleaning this mess up, and this will clean up. So what we're going to do is I'm going to write this as 2x, and I'm going to go ahead and put the back into square root so it looks a little bit nicer. Plus, this is going to be x squared over 2 square root of x squared plus 1.
Okay.
Because this is a negative power here, right?
Yeah, yeah,
That drops to the bottom and it becomes a
yeah,
square root on the bottom.
yeah,
This is on the top, 2 is on the bottom. Okay.
yeah.
Now you can actually clean this up even more. Because if I want to get common denominators here, I need to multiply this by that thing on the top and
Yeah.
bottom.
Okay.
And when I do that, it'll actually clean up pretty nicely. So I'm going to show the work in yellow over here. I'm going to multiply this on the top and bottom by 2 square root of x squared plus 1. 2 square root of x squared plus 1. And that way I'll have a least common denominator.
Because yeah, the other side you only have to multiply by 1, right? Because
Yeah, it already has the denominator. So this cleans up into, watch what happens. This turns into 2x, I'm sorry, not 2x, 4x, because the 2 times 2 is 4,
yeah,
times, and the square roots just go away here.
yeah, exactly. Yeah.
Plus x squared, because that's at the right over here. And it's all over. Now I have that common denominator of that, which simplifies even further. If I distribute that 4x in, that gives me 4x cubed plus, now I'm going to put in standard form, decreasing, right? Plus x squared and then plus 4x.
Okay.
You got how I did that?
Yeah.
All over 2, the square root of x squared plus 1.
Boom.
And that's a nicer looking way to write that.
Yeah.
Because now it looks like just a rational function.
Yeah.
So for example, if you wanted to take the derivative again, for example, if you wanted the double derivative, it's much easier to do that when it looks like this than when it looks like that.
Yeah. Yeah.
Maybe not much easier, but it might be easier.
Yeah.
Is that how he wrote his answer?
Yeah. I looked at it like before we had finished. Yeah. That's how it is.
So he did.
No, wait, he forgot he doesn't have a 2. His is 3x cubed plus 2x over x to the square root x squared plus 1.
Whoa. Tell me what it says again.
Here, I'll screenshot it.
Oh, just tell me, I'll write it. It's okay.
So this is a fraction, 3x cubed plus 2x over square root x squared plus 1.
That's his answer, his final answer?
Yes.
Jeez, did I make a mistake here? Those are radically different.
He multiplies the 2x on the outside.
Let me just go back through and see if I made a mistake ever. So it's because it's very easy to make mistakes on these. So we wrote that correctly. So I'm going the derivative of the outer one times the inner one plus the first one. Sorry, I didn't mean outer. I meant first and second. The first one times the derivative of the second one. So the derivative of this is going to be 1/2 that. Oh, I did forget something.
I think he put.
I didn't do the
2x on
chain.
outside.
I didn't do the chain rule. You see what I forgot? I forgot to take the derivative of this and multiply it. So that's 2x.
Yeah.
So yeah, I did make a mistake. Okay, so let's go back and fix that. So this is going to be x cubed here. See if we can just clean it up. That's going to be x cubed, and the 2 is going to cancel. So there's not going to be a 2 here because there's 2 and the 2 will cancel this. So I don't need this 2 here. But I still need the everything else. So this is not 4 anymore. That's 2.
Yeah.
And this is not x squared. Oh yeah. Okay. Yeah, I definitely made the mistake. So this is x cubed, and that means this thing is going to clean up. I don't need that 2 there.
Anymore.
And then I'm going to get 3. Yep, that's right. 3x cubed plus 2x. Yep. Wow, one little mistake. I forgot to take the derivative of the inside, but that made all the difference in the world. Interesting. Okay, good. Yeah, it's very easy. It's like I said, it's very easy with calculus. That's the thing. That's why calculus has such a bad rap with people, is because it's one, you do so much work, so much tedious work, and if you make one tiny mistake, then you get it wrong. So you really have to be very, very cautious and double check and all that kind of stuff. All right, use the calc. Oh, they want to use your calculator to find.
Yeah.
Do you know how to do that?
Yes, I do know how to do that. That's not hard. Actually, that's really easy to do.
Right.
Maybe we don't even have to go over that. I just do math 8 and then like you put in the derivative and then that's easy.
You got it.
You can skip that.
Okay. Find the equation.
I think he's referring to the other questions, by the way.
I can't make this smaller. Can you make it smaller?
I can mess with it if you want. Real quick.
I don't know what's happening on my iPad, but it's not. Jamboard is. It's not giving me
better.
I think the problem is that it's just not updating. Yeah, that's good. Find the equation of the line tangent to number 10 at x equals 1 and the equation of the line normal to 11. So was this 10 and 11?
Yeah, maybe I should just copy and paste this, delete this page.
No, it's okay. I got it. So basically what you're doing is once you find these things, number 10, you're finding the derivative at 1. So for number 10, you already found the derivative at 1. Whatever number that is your m. And so the equation of the line, I have to find a point. And the point is going to be 1 comma. So plug in 1 here. So f of 1 is going to be plug in 1. You're going to get 7 over e to the third. Does that make sense? How I came up with that?
Yeah.
So whatever you get for your slope on number 10, you just write y minus y sub 1 equals whatever you got for m. Times x minus 1.
Okay, that's easy. Okay.
Yeah, and for number 11, they say find the equation of the normal line.
That's with like the slope being like the negative reciprocal, right?
That's
the
right.
last unit, okay.
So when you find the slope of that, when you find the slope of that, then you just do -1 over m.
Yeah,
And then again, find the point, 1 comma, let's plug it in, 1 comma ln of 2. And then write your equation, y minus ln of 2 equals -1 over m times x minus 1.
okay,
So just, I'll call this m10 for the slope of 10, and this is the
Yeah.
slope of 11.
yeah,
Got it?
yeah,
So you can go through and do that
yeah.
on your own.
Will these be a lot of work?
For number 9 you're talking about?
12 through 14.
I'm sorry, 12 through 14? I don't know, let me look at it. Determine if it's continuous, differential, both and neither at the indicated values. So continuous means that, continuous would mean that when you plug in f of 3, for example. All right, let me just write this for number 12. Continuous, if f of 3 in the first part equals f of 3 in the second part.
Okay,
In other words, if you plug this into both of these equations and get the same thing, then it's continuous because you don't jump. Continuous means you can draw the graph and you won't have to lift up your pencil. So
Yeah.
this first one's is a line from 0 to negative infinity. That's a line. So let me just do a quick sketch of the graph here. So from at x equals 3, here's 3. It's a line from 1, 2, 3, 4, from 4, -3. Oh, sorry, I did that wrong. It starts at -3, right? And it's got a slope of 4. So I go up 4 over 1, up 4, 4 over 1, up 4, 1, 2, 3, 4 over 1. So this is going to be my point, and it would have been an open circle, but that's just a line. So the question is it continuous? Well, if I plug in 3 here, I
Yeah.
get 12 minus 3, which is what?
9.
9. And if I plug in 3 here to the second one, what's 3 squared?
9.
It's also 9. So really what I'm doing, notice what this graph would have done is this, right?
Yeah,
That would be a parabola. So really this is just a parabolic right there. It's just a parabola, but it happens to be at that same point.
yeah,
So is it continuous? It is continuous because you never had to pick up your pencil.
yeah.
So the function is equal in both places. So that's how you find out if it's continuous.
Okay.
So continuous, yes.
What does differential mean exactly?
Differentiable means you can take the derivative at that point.
Okay.
Um,
When are times when you cannot take a derivative with that?
I know I'm actually trying. I was wondering if you have notes on this because I'm trying to remember.
We haven't had like a question where it wasn't differential or whatever. It was weird. We haven't had that yet.
Well, I want to say no, because those.
Is there something like a -4?
So from the problem with differentiability is it has to be like, how can you say what the slope is? What's the rate of change at that point? See how the rate of change on this graph would be like this, and the rate of change on this graph would be like that.
Maybe it's like a quadratic because it's like 0 at that maximum point. Do you know what I'm saying? Like for
So my gut feeling is if we take the derivative of both of them, our derivative of this is going to be 4, and of the first part of that piecewise, and the derivative of the second part of that piecewise is 2x. And if I plug in 3, I get 6 for this one, and I get 4 for this one.
Yeah.
So they're different, and I believe that's how you tell. I think you take the derivative and then you plug it into both of them and see if that.
Okay, wait, so if it's different, is it good or bad?
If it's different, that means it's not differentiable, I believe.
Okay, that makes sense.
But I was wondering if you had notes on that.
We haven't gone over it that much. Yeah.
How to tell if function is differentiable
Or not.
at a point. A function is considered differentiable if the derivative exists at each point in its domain. But what does that mean? It means that a function is differentiable everywhere the derivative is fine. So as long as you can evaluate the derivative at every point of the curve, the function is differentiable. So how do you prove it's not differentiable at a specific point? You can do the side limits.
Okay.
Yeah, that's not, I don't know if that's it.
Side limits. That kind of makes sense.
I'm gonna say, how do you tell if piecewise function?
Yeah. Just saying, since we do have 15 left,
Yeah.
Let's just go over 22 and 23 because I don't really know them that much. And then whatever extra time we do have left, we can go over other ones. But I know how to do those other ones kind of.
Okay, so I found a video on it from Khan Academy, differentiability at a point. And what they're doing, they are taking the limit as x goes to 3 of f of x.
Mm-hmm.
Yeah, let me see if I can. Let me share this screen instead.
Is the function given below continuous / differentiable at x equals 3, and they've defined it piecewise, and we have
Let's just skip through.
Now, what is f of 3? Well, let's see, we fall into this category, this case right over here, because x is equal to 3. So 6 times 3 is 18.
He crossed off not continuous because he knows it was continuous.
Yeah.
He could actually say, he could cross off the bottom one too.
Yeah.
It says neither.
Is 9. So this is 9. So the limit of f of x as x approaches 3 needs to be equal to 9. All real numbers, so we could just pop a 3 in there, and you get 18 minus 9. Well, this is also equal to 9. So the left and right hand limits both equal 9, which is equal to the value of the function there. So it is definitely continuous. So we can rule out. So let's first think about the limit as x approaches 3 from the left-hand side. So it's over.
So he's
x
using
minus
the
3,
old school
and we have f
rule
of
of
x
the function
minus 9.
derivative.
But as we
function.
approach from the left-hand side, this is f of x. As x is less than 3, f of x is equal to x squared. So this would be, instead of f of x minus 9, I'll write x squared minus 9. And x squared minus 9, this is a difference of squares. So this is x plus 3 times x minus 3. X plus 3 times x.
I don't know why he's not just
3.
doing the derivative.
And so these would cancel out. We can say that this equivalent to x plus 3, as long as x does not equal 3, that's okay because we're approaching from the left. And as we approach from the left, well, x plus 3 is defined for all real numbers.
Hold on, I'm trying to think of what he's trying to say. He's saying he's going from the left, so he's using x squared. But why is he writing x plus 3? I'm actually confused at what he's trying to do here.
Yeah, same here. I was confused when he started doing the fractions.
So first of all, we know what f of 3 is. F of 3, we've already evaluated this. This is going to be 9. And let's see if we can evaluate this limit, or let's see what the limit is as we approach from the left-hand side and the right-hand side. And if they're approaching the same thing.
So what he's doing is he's finding the limit as x goes to 3 of f of x of the rise minus the run. You remember that the rule for that, for the original rule for derivative. But I'm wondering if why he's not just using derivative.
Yeah.
Why he's not just taking the derivative.
Same thing that they're approaching is the limit. So let's first think about the limit as x approaches 3 from the left-hand side. So it's over x minus 3.
So he's doing the left-hand side
f of x minus 9.
So that's this.
So as we approach from the left-hand side, this is f of x. As x is less than 3, f of x is equal to x squared.
Oh, that's
so
why
this
he's
would
putting
be
x squared.
Instead of f of x minus 9, I'll write x squared minus 9.
Because the 9
and x squared minus 9, this is a difference of squares.
Is the value.
So this is x plus 3 times x minus 3.
Okay, I get what he's
plus 3 times x
minus
3.
Okay, I see what he's doing.
And So these would cancel out. We can say that this equivalent to x plus 3, as long as x does not equal 3, and that's okay because we're approaching from the left. And as we approach from the left, well, x plus 3 is defined for all real numbers. It's continuous for all real numbers. So we can just substitute the 3 in there. So we would get a 6. So now let's try to evaluate the
Which
limit
is what we would have gotten as
as
well.
we
If you
approach
just took the normal
from the
derivative,
right-hand
we would
side.
have gotten 6.
Okay.
I don't know why
Once
he's,
again,
maybe
it's
he
f
hasn't
of x,
taught
but as we
the
approach from the
shortcut for
right-hand
finding
side, f of x
derivatives.
is 6.
He's using
Yeah,
the
that makes sense. That makes
That's
sense.
our f of x.
You know what I'm saying?
And then
Yeah.
we have minus
So
f
he's
All the
of
video, the dude like talking over you
6x minus
at the
8.
same time.
Yeah, he's just using, so we could have just taken the derivative, which is 2x,
Yeah.
and plug in 3 and you get 6.
Yeah.
And then for this, take the derivative of this, you're gonna get 6, basically. So
Yeah.
for this one, it is going to be differentiable because they're both gonna be the same.
Okay.
But
So
for
taking-
our example, it's not because the derivatives are different.
Yeah. Okay. That makes sense.
So for his, he's gonna say yes, but for ours, we're gonna say no.
Okay.
You understand why? Does that make sense?
Yeah. Yes, that makes sense.
Okay, so back to my screen. So which ones do you say you want to do? We got about 10 minutes left.
Pages 14 and 15. 22, 20.
Okay, so you're okay with how you do these now? So you're going to say differentiable no, because when you take the derivative, when you take f prime of x, the first part of it is going to be 4, and f prime for the second part, the derivative for the second part, it's going to be 2x. And when we plug them in, oh, I already wrote that to the right. When we plug those in, when we plug it in for f prime of 3, you get 4 still. And when you
Yeah.
plug it in for 3 here, you get 6. And so
Yeah.
no,
Yeah.
not differentiable.
Yeah.
So that's how you're going to do all of those as well.
Okay. It's probably gonna be a multiple choice question. Makes sense.
Probably, but let's just real quick do them now that we see. And if you have the answer key, this will also help us know we did it right. So let's take the derivative
I
of
might
it.
just want to use those as practices though. Like we only got 8 minutes. I need to go over 22,
Okay.
23.
So 2x and 4 and then plug them in. All right, good. What page you say you wanted to go to?
22, I mean pages 14 and 15.
Okay. So this, we're doing word problem type thing. Height in meters modeled by this equation where t is in second. Find the height of the sand at t equals 2. So just basically you're plugging in. Yeah, you're just plugging in 2 for this one. So h of 2 basically,
Yeah.
which is just sine of 1/2 times pi times 2 pi plus pi over 2 plus 2. So that's sine of 1/2 of,
Oh, that's easy. Yeah.
right? You can do that, right? You just use
Yeah.
your-
Yeah. I know Patrick, don't worry.
How much sand was added to the pile during the time from t equals 0 to t equals 2? Let's see, the height.
Oh, do you just subtract h2 minus h0? Wait, no.
No, because they're saying the height is modeled by that, but how much sand would be volume?
Yeah. Yeah. Make it easier.
So
I got it.
I don't know how the volume is related.
Wait up. Let me just download it. It's like,
You know what I'm saying? I don't see an equation for volume.
is it just length times width times height?
Well, this isn't a square. It's a pile of sand.
He did h2 minus h0. That's what he did.
How much sand is added? Well, I mean, that's going to tell you the difference in the height.
Yeah, he just did h2 minus h0.
So, okay, it's kind of weird to me. That doesn't make sense to me.
Yeah.
Because height is not the same as volume. And when they say how much sand, I'm not thinking how many inches higher.
Yeah.
I guess that's what he means.
Yeah.
So it's just h2 minus h0.
Yeah.
So yeah, find those. And is the pile getting taller or shorter when time equals 2?
You just use the derivative, right? To know the slope of the derivative, because like you'll know like the increasing of a graph.
Correct.
Okay, that's okay, that's easy then. Okay. Wait,
Yes.
actually, okay. Let me just try to find the derivative. So sine half.
Okay.
Will this be a this is a long equation. Okay, wait a minute. The +2, like, is it product rule?
No, because it's not being multiplied.
Is it chain?
Yeah, all you're doing is you basically have sine of u. So the derivative of that is just cosine u times du.
Okay. Okay.
So it's going to be cosine. So the derivative of this is going to be the cosine of 1/2 pi t plus pi over 2. But then the derivative of 2 is just 0.
Oh,
So you actually don't add that in there.
okay.
So that's the unchanged part. You see how I took the derivative of the outer function.
Yeah.
I really have two. I have taken the derivative of this, and I'm then separately taking the derivative of 2. So the
Yeah.
2 doesn't matter. I'm
Yeah.
basically just finding the derivative of this.
Yeah.
You understand?
Yeah.
So then I'm going to multiply that by the derivative of the inside function,
Mm-hmm.
which is just pi.
Yeah, there's pi over 2 is not a derivative, and then t.
Because
Yeah.
pi over 2 is constant. That's right.
Yeah. Okay.
So writing it simpler, it's pi times the cosine 1/2 of pi t plus pi over 2. That's the derivative.
Okay.
So the rate of change, yeah, you're seeing, is it going up or going down? Is that a positive or a negative value when you plug
So
it
then
in?
you just insert 2 into that, right? So that's
Yep, and then punch it into your calculator.
okay. That makes sense. Okay. That's not that bad. Okay. All right, then 23. That'll be our last one.
Number 23, it says, given the graph below, state all the points where the function is continuous but not differentiable. Okay, well, it's not, it's continuous everywhere. If you look at the graph, it's basically continuous everywhere except here and here,
On the asymptote.
right?
Yeah.
So this is where it's discontinuous.
Mm-hmm. So the points are 3 and 5.
Well, no, because that continuous but not differentiable. So
Oh, continues.
it's not continuous here and here.
Okay,
So continuous would be anywhere else. So where is it not differentiable? And I believe it's here. Do you talk about like
that I was saying like that those areas are not differentiable because like those derivatives are 0.
well, the derivatives are different from the right and the left. That's the reason. If you're coming from the right, that's got a negative derivative, and if you're going from the left, it's got a positive derivative.
Okay.
And it comes to a point.
Okay.
So that's where it would be not differentiable,
Okay.
or that's why it's not differentiable there.
Okay.
But it is continuous here.
Okay.
Some of these points over here.
So is it -2 and 2 and
I think it's just -2 actually. No, because at 2, it's still differentiable here. The derivative at this point, see how it's just a curve?
yeah.
The derivative at a peak is just 0.
Okay. Okay.
Because it's smoothly going from that and at just that point.
Okay. Okay.
But for here, at that exact point,
yeah.
if you're looking at it from the right, it's got a positive. If you're looking at it from the left, it's got a negative slope, and from the right, it's a positive slope.
Yeah. Yeah.
Does that make sense?
Yeah.
So I think the answer for this is only at x equals -2.
Okay.
Do you have the answer key?
Yeah.
Yeah, let's check it while we do it, because this stuff, to be honest with you.
It said -2 and 7.
Okay, so that was the other thing I was going to check. over here, you've got some things right here. This is an inflection point.
Okay.
Or this is, so 1, 2, 3, 4, 5, 6. Yeah, this point right here.
Is an inflection point.
Well, it's not really an inflection point. It's like it looks like it's kind of hard to tell.
Mhm.
But I'm trying to think of what the reason for that is. That's why I was wondering if you had notes.
They're up in my room. All in a notebook.
So continuous but not differentiable examples. This is the best way to do it.
Okay. Shoot, do you have a session next, like thing?
Yeah, I do. I'm trying to look it up. It probably says in your notes. I can't remember what they're called.
Mhm.
But there's actually some nice videos about it too. If you look it up, just type in continuous but not differentiable. There's some nice videos on YouTube that will explain it, and the reasons why also.
Okay. And C, I'm guessing it's
Here we go. I found it. A cusp or a corner. So this would be a cusp, I believe.
okay.
Oh, and then a vertical tangent. That's what this is called. This is called a vertical tangent.
Okay.
Couldn't remember what it was called. So that the reason is because it's a vertical tangent.
Mhm.
And this is a cusp. This is a cusp, or it might be a corner. I can't remember.
Mhm.
Can't remember which one is which, but that's a cusp or a corner.
Okay.
Those are the examples of things that would be. So like an absolute value function would also be that way.
Yeah.
Okay.
I'm guessing.
So then the other question is differentiable but not continuous. A whole might be differentiable but not continuous.
I think it's 3 and 5. I'm very sure.
3 and 5 shouldn't be differentiable. Did they say 5?
3 and 5 are C.
Oh, the answer. Yeah, no. How about letter B? What was the answer for letter B?
No, there was no points.
None.
Yeah.
Okay, I was thinking that maybe this whole would be considered a removable discontinuity, pulling it straight out. Oh no, because for differentiable, it has to be defined at that. That's why. Yeah. See, I haven't done this in a while. I'm gonna have to go back and review this. I don't typically tutor BC Calc, so.
Okay, it's AB, but yeah.
Oh, this is AB.
Yeah.
Oh, you guys are flying through this stuff. Yeah.
Yeah, I think we're ahead right now.
Yeah, you guys seem like it. Anyway, you feel good about this?